Ladies and gentlemen, please welcome AIAA Executive Director Sandra Magnus.
Good morning, everyone. Okay, we're going to do this again. Good morning, everyone. Much better. You guys should be all energized. It's Wednesday. There's exciting things going on. You've had 2 good days of content and information, and we've got 3 more days to go, or almost halfway through, and it's very exciting. So welcome to day 3. I was wandering around the exhibition hall last night during the reception, and there was quite a lot of energy in the room, and it looks like you guys were all having some wonderful conversations. We have such a good mix of government, industry, academia, all different sectors of the industry, so I hope you were able to meet some new friends, greet some old friends, and have some really good discussions about things that are going on. I'm sure a lot of new ideas were generated and a lot of great conversations were had. Today, the luncheon at 12:30 is in the exhibit hall, so please make your way down there and spend some time with our 50 exhibitors, and there's some great things there they have waiting for you to discover as well. Also, for those of you who were at the awards luncheon yesterday, there were a lot of people recognized for their contributions, whether it was lifetime contributions or best papers or technical thoughts. So congratulations to all those award winners. Our second awards luncheon will be on Thursday at 12 p.m. I do want to take a moment to talk about the AIAA Foundation. You're hearing a lot about that this week because it's 20 years old this year, and we're doing a special fundraising program. We're trying to see if we can get $20 from quite a lot of people across the Institute to continue some of the great things we're doing with the foundation. We fund a lot of our undergraduate and graduate award programs there, the student paper competitions, which give undergraduates a chance to practice their presentation skills, and the winners actually come to SciTech to compete, and we fund that travel, as well as our Design Build Fly competition, which it's incredible. They had over 140 entries this year, and we get undergraduates from worldwide that show up at the Design Build Fly. It's a wonderful competition, and I don't know how many of you have been exposed to it. I go every year, and it's really great to see these undergraduates coming with these small airplanes they built and getting them out on the flight line, and it gets into some heavy drama as we watch and see whether their planes will take off or whether they will take off and then crash and then have to go back and get rebuilt. It's really a great experience, and we fund that out of the foundation as well. So if you're interested in donating $20 to the foundation, there's some envelopes around and down in the AIAA Pavilion, and I encourage you to just consider it as sort of a Christmas present to the AIAA Foundation. Also, some housekeeping items, and then we'll get started. As you're aware, we've got the conference IO, AIAA.cnf.io, and on that, well, you can also find an extended bio for our speaker, so I won't be going into the details of that. We have a Twitter contest, so for those of you who are into tweeting, I heard we were number 3 trending in Washington, D.C. earlier this week, so people are paying attention to what we're doing here, as they should. The hashtag is hashtag AIAA SciTech. There's an Apple Watch on the line for the winner. And then following the keynote, I'll get up here and just sort of go over the rest of the day with some reminders. So with that said, we're going to launch right into our opening plenary this morning. Thank you for coming. And what we're going to do is look at the DoD engineered resilient systems and how new tools and processes can streamline the design and manufacture to improve the resiliency and usability for all end users. And to get this discussion started, we're very happy to welcome Jeff Hollland, Director of R&D and Chief Scientist of the U.S. Corps of Engineers, U.S. Army Corps of Engineers, to the stage. So Jeff, it's all yours.
Engineered Resilient Systems, or ERS, is developing capabilities that will transform how the DoD designs and builds the next generation of defense systems. ERS is setting the stage for how acquisitions will be done in the future by providing greater accuracy in modeling designs through tools that allow us to gain deeper insights from data. As a result, better decisions produce better systems. ERS is working to evaluate big data quickly and efficiently, create visualization techniques that produce significant design insights, and use high-fidelity physics models to improve accuracy of results. These tools help decision makers better understand design options, such as capabilities and mission effectiveness versus lifecycle cost. This allows the acquisition community to focus on the resiliency and versatility of a system, as DoD missions are rapidly changing and evolving despite shrinking budgets. ERS is bringing together engineers and scientists across the DoD, industry, and academia to develop and use these tools. The result? Better ships, better aircraft, and better ground vehicles, all financially sustainable into the next century.
All right, now here's the first thing that you should ask yourselves as you look at that stuff. First, you should ask yourself, have you just gone through a piece of Department of Defense propaganda? All right, all those thinking that you have, raise your hands. You can do that. I can't see you anyway, so it doesn't matter. Those of you that raise your hands that are members of the Department of Defense, shame on you. Go outside and stand by yourselves. Those of you that are actually members of my team, your money is now cut off, so you can go stand anywhere that you want to, okay? Those of you that are my age, I'm almost 60, will undoubtedly remember the Gemini space program, and you'll remember that in the 60s, there were pictures on the old CBS, NBC, ABC. You remember those channels? It showed the guys doing spacewalks, and it showed NASA animation. You remember that, folks that are my age? My mother would always ask me this. She would ask, how are they getting the pictures of those guys out in space like that? That is amazing how they're doing that. And I would say, even as a 10-year-old, Mama, that's animation. And she would say, oh no, honey, they wouldn't put that on TV if they weren't actually filming it, okay? I gave up after a while, and my mother would giggle to herself in the background. What you just saw is, I guess, our modern version of NASA animation from 1968, 1966. And so the question is this, is there anything behind it? Okay, because even advanced scientific visualization today can often be done by 10 and 12-year-olds. The question is there any meat behind this carcass that I'm describing to you? And what I'm going to do over the next few minutes is show you that there is. So here's what I'm requesting from you. Give me 10 minutes, and in 10 minutes' time, if I can't show you that, if there's a break someplace, you can all run to it, okay? And AIAA will buy you a croissant. And the AIAA president will pay for it herself. She told me to tell you that. Okay, see, I told you I was not going to be boring. See, are you with me? You're still with me so far, okay. Okay. Now, you know, if you know anything at all about acquisition and the things that go on in the Department of Defense, you know a couple of things that are really pretty vitally important. First off, you know that the programs of record that we have within the department are extremely long. For example, the C-130's been around for a long time, but my favorite one's the B-52. I believe it's fairly accurate in saying that the B-52 flew for the first time in 1953. If not, it's very close to that time period. Some of you, in fact, may have worked on that from the very beginning, but what we do know is this. The B-52 has been modified, retrofitted, advanced, enhanced, pick your own phrase, multiple times through its lifespan for weapon systems and for new missions for which it was never intended originally. If we had had a capability to consider even some of those ideas, not all of them certainly, but some of them, some of the new threats, some of the new mission spaces that might have been under consideration for the B-52. The question or the hypothesis placed in front of us is could we have designed the B-52 or retrofitted it in such a way so that we would have spent much less money doing that retrofit and have been more flexible, more resilient in that process? Hang with me as we go through this. The 20th century process of engineering, certainly as practiced within the department and perhaps practiced elsewhere, is one of perhaps a very linear process, and at times one step forward and two step backward process. That process, the DoD 5000 process, is often thought of as a process that's actually shown on a slide in a couple slides over. It's often thought of as a process that advances forward in a very deliberate fashion, but that process is often disturbed, if you will, by new requirements. And because of its length, often being 20 years in length, those new requirements perturb that system quite significantly, so that the process becomes one of more of a V or a series of Vs, rather than a simple linear process along the way. The process is very hierarchical in the sense that often subsystems are often designed, if in parallel, wonderful, but often in series. That results in a stovepiped capability for the designs themselves. There are a number of interfaces between those systems. Many of those interfaces are highly customized. They're not modular in any sense of the word, and they certainly are not open in any sense. A 21st century way of doing this, in order to speed that process up, has all of the characteristics that are shown in front of you there, and requires a construct that allows us to be open while simultaneously respecting intellectual property, something that many consider to be the very antithesis one of the other. You can see how we have done things in the previous 10 to 15 years, and I would say probably you could consider that to be since the Second World War, in terms of the way we have done design, the way we have done acquisition in general. But if you look at the way that we will have to do that in the future, I would submit to you that the way we have done it over the last 40 years may in fact be untenable. Flexible platforms will absolutely be needed. The ability to be able to snap, for example, one weapon system off of one platform and potentially snap it onto another becomes very important. Now, for example, just within the Pacific area of operations, there are, half a dozen climatic regions alone that have to be considered. The pivot back to the Pacific region all by itself reintroduces something that, except for mountainous areas, the United States military has not concerned itself with for a long period of time, and that is snow and mud. Okay, we are worried about wetlands again, something that we have not concerned ourselves with for a while. We are suddenly concerned about opposing air forces again, which we have not honestly, in many ways, been concerned about since Vietnam. In order to be resilient to these threats and others and not have to design a brand new aircraft, for example, each time we face a new adversary, we need that resiliency to be able to go from one area to another to another. Now let's look at these issues. We know that cost is something that we hear about all the time. It's in the press, it's there all the time for us. But I want to draw your attention to the areas that are down on what is, to me, my left. We know that there are very rapid and emerging threats. Those threats are occurring sometimes what seems to be a nearly daily basis for our nation, but if not, certainly on a semi-annual basis, it seems. More importantly, technological change is occurring on a dramatic fashion. If you were to just simply look at the idea of how computers change, even if you believe that Moore's law has almost reached its complete potency and that it's about to turn over completely, just look at how many times computers will change within the lifespan of a 20-year program. Let's say it changes at least 8 times. Let's say 10. That's 10 orders of magnitude potentially in computer technology that could have changed, or at least 10 realms of change of computer technology within the realm of one program of record. That's 10 computing capabilities that need to then sit inside of one design. If the design were plug and play, that would be no problem, and yet that design is often not plug and play. The result of which is that when each new capability needs to go back in, its form and fit often does not take the place of the form and fit for which it is making the replacement. That is particularly true for weapons systems. If we look on a surface ship and we look at the idea of what a railgun is going to do on a surface ship, I can assure you that today that no railgun has been designed to take the place of anything on a surface vessel. And that the idea of where a railgun would go on a surface vessel is very tough for those surface vessels. You can apply that to any airplane, any rotorcraft design that you can think of equally well. In terms of extending the lives of these capabilities, we can see that we have a tendency to extend the lives of all of our capabilities well beyond their initial design lives. The normal lifespan of a surface ship, for example, is 30 years. We're probably going 40. We look at our aircraft, and our aircraft are going, 40 years potentially in many cases. Apply that to the bridges that you have driven over to get here today. And suddenly here in Southern California, those bridges are very important during an El Nino year. I drove from China Lake yesterday to get here. It was quite an experience to drive through Southern California and experience what is a normal rainfall pattern for central Mississippi, which is where I live. Then you have the workforce decline problem that we have and just the simple, straightforward act of attrition. I will be 60 in March. The last time I looked in my adult choir in my church, I was the third youngest member of my bass section. That's not good. That's really not good. And since I started as a tenor in my choir, you can see that we are systematically working ourselves out of capability over time. Okay? We need to be able to get people up to speed on what they're doing much more quickly than we have in the past. Now here's the DoD 5000 process, and here's what I'm going to propose to you today as the way that we believe in the Department of Defense from a science and technology perspective, not a policy perspective, because I'm not a policy person. Okay? And I will make that disclaimer to you today. I'm a science and technology individual. Okay? So if I say something remarkably stupid, it goes on tape, it's shown back in Washington, someone runs to the Hill before I can get back to my phone, then I'll tell everyone I'm a science and technology guy, which is a euphemism for I am really well educated and remarkably stupid. Okay? That has covered me very well for 37 years that I've been in the federal government. I'm hoping it will cover me for a little while longer, at least through the end of today. All right, so here's the DoD 5000 process. That process, there's nothing wrong with that process in and of itself. Okay? It's not what it says, it's the way in which it is implemented. Okay? So how is it that we go about speeding this process up? One primary way that we can speed that process up is to move heavy engineering within that process hard to the left in the process. And the question is, how can that be done? How can we do much more intensive engineering in this process earlier in the process? And how can we learn from that heavier engineering much earlier? How can we save information within that process and learn from it all along through the process? And how can we maintain, through knowledge management and data analytics, information as we go so that requirements and data drive our decisions instead of decisions early on driving all of our decisions later on? If you were a systems engineer or if you were using systems thinking, you would think that what we were talking about is basically the idea of using the idea of set-based design instead of point-based design, and you would be absolutely correct. But the ability to do this is very different It's almost counterintuitive from the way many of the designs and alternative analyses are presently done within most of the design and alternative analysis community within the department. For example, and I know this is AIAA, but I would like to use the example of a ship again as a simple example for you. Many times in naval architecture, one of the first things that's ever decided is what the basic shape and design of the hull is. That's a seakeeping decision that's fundamental to the design. Once that basic volume, if you will, and the shape of that volume is designed, that's often locked in. And that will be something that is specified. There may be 2 or 3 of those, but that basic design will be there. And then, in a sense, all of the functionality that goes with that ship is, in essence, utilized within that volume until a number of things happen, one of which is until the radar cross-section of that vessel gets to the point where it becomes large enough that it can be seen from Venus, in which case it's clearly too tall. Okay? That's clearly a problem. From a functionality perspective, what you would really like to do is to carry perhaps 10, 20, 30, 50 of those vessels forward. Perhaps you'd like to carry 1,000 of them in your design space. Perhaps you'd like to carry 5,000, 10,000. Perhaps you'd like to create a trade space in which you can consider many, many, many different trade-offs between, in the case of a ground vehicle, between lethality, survivability, maneuverability, mobility, and then what I'll call efficiency, power efficiency, just those 5 things. And there are many, many, many other factors. You can apply the measures of effectiveness that you have for an aircraft accordingly. Okay? The question then is can you do that in the same wall clock time from a productivity perspective that you do the one design today? Because if you cannot do that, then people will not use it. And can you do the data analytics that are necessary to turn that into a decision? Because if you cannot do that, the program managers and the program executives that have to make these decisions will not be able to fit that into their business process so that they can effectively use it as well. I believe that you can. By combining the advanced modeling capability that the department has, and by working with industry in particular to maintain their intellectual property while connecting to that intellectual property, excuse me, by connecting with the ability to evaluate what I'm calling context simulation, which is how do we warfight this? How do we evaluate whether a particular piece of material will operate? How will it operate in a warfighting setting? By putting all of this up on our high-performance computing resources, because the particular aspect that I'm talking about requires the high-performance computing capabilities. And I'm very fortunate that my organization leads the Department of Defense High-Performance Computing Modernization Program, and I've grown up with that program. So I know that program very, very, very well. It's something that I've done for 30 plus years. Then coupling that with what we're calling here mathematical optimization, but really what we're talking about straightforwardly is Tradespace analysis. And then putting that together in both open environments for certain classes of problems and trusted environments for classified problems. Can you put that together with an architecture that allows you to do the analyses that you need to do in the time that they must be done? And can you do tens, dozens, hundreds, thousands, potentially millions of analyses? Can you keep those data in what would become permanent databases and continue to analyze those databases such that they become national resources for, in this case, the Department of Defense, and that information then becomes a resource to councils of colonels, councils of captains, to give real information to them to do what-if analyses and trade-offs when they're making deliberations on what's the worth of this margin, this capability, and this capability. We've done that, or at least we've started. A combination of people in the Army, Navy, and Air Force have come together to build a first capability to do that. The fact that the Army, Navy, and Air Force are working together to do this with the Office of the Secretary of Defense is miraculous. Those of you that do not understand the miracle of that should ask someone. This has been submitted for consideration for sainthood and is receiving strong consideration. Okay, just the fact that we're talking to each other. There's an Air Force guy sitting right there. He could give my slides. Okay, he really could. His name is Ed Kraft. I even know his name. Right, Ed? Do your head like this, Ed. Okay, I paid him $80 to sit there today so that he could. He's just a guy off the street. I had to buy him a suit and everything. Okay. It is amazing that this idea has come to fruition. What has empowered it? The fact that we own the computing capability, but the fact that we own some models that we believe in that are verified and validated. I would submit to you that if we did not own the process models that we have, which have been verified and validated over the last 10 to 15 years, I'll talk some more about those in a minute, that we would not have the ability to do this. For example, if we had no ability to model anything at all that had to do with, let's say, how airplanes fly, and if we did not believe any of that at all, then if we coupled highly uncertain modeling capabilities with Tradespace analysis, with an understanding of the environment, with the ability to war game that, to war fight it, then what we would wind up with is 14 or 16 and a half decimal places of accuracy of absolute baloney. But because it would have 16 and a half decimal places of accuracy, it would have been run on a supercomputer, and it would have really cool graphics like what you saw at the beginning. Someone would believe it, and the result of that would be that it would be dangerous. Okay? And that's unconscionable. Okay? But that's not what we're doing. We're putting as much energy into understanding the modeling work that we're doing as we are into the rest of it. But what I'm here today to tell you is that anything that I believe very strongly, that anything that we can model well and believe that we're modeling well, we can put through this Tradespace analysis concept, and we can believe the results of what we're seeing. Conversely, anything that we do not believe we model well, we have to be able to understand the uncertainty that we are dealing with. And if that uncertainty is extremely large, and if it swamps the analysis, then we have to admit to the fact that that uncertainty is swamping the analysis. Okay? We have built this construct. It combines, under one architecture, an open architecture, by the way, a trades analysis capability. There's more work to be done on that for sure. An advanced modeling capability built around a set of tools that are called CREATE. CREATE is a component of the DoD High Performance Computing Modernization Program. It was the brainchild of Dr. Doug Post, who's seated right over here. If you want a lot of details about that, Doug will be happy to talk to you about that a little bit later. I've got a couple of slides on that. There's an entire website about CREATE. And I'll show you just a few slides as time permits. There are many other models that need to go into the capability, and part of the Defense Department's challenge is to figure out which of those models needs to go in, because we do not need to accommodate every model in the department. There's an environmental representation piece that has to do with the idea of actually modeling the material in the real world. If we want to know how something's going to drive down the street in an urban environment, we should represent that actual urban environment. Many of those environments will be classified, admittedly, okay, but we should actually have the real world digitally represented to the level of abstraction required. And we're capable of doing that. There's a mission context component of this that has to do with modeling the actual missions. That's a wargaming or simulation component. And all of this, again, is combined together under an architecture. We've integrated that under a workflow capability that mimics the actual business or process flow that the program managers themselves have. We have done this thus far with a couple of examples, and I'll show you the examples of what we've done thus far. And we've done this to support requirements generation, which is a major effort to try to refine and get more feedback into requirements. Like almost any software project, the better we do with requirements, the better we will do in getting a good answer. And most of our weapons systems, quite honestly, are huge software projects in a very, very, very real sense. We've been working on analyses of alternatives, and the next area we'll be going into is virtual prototyping. Earl Wyatt, who leads the Department of Defense's prototyping world, has made an investment in this particular effort to begin the process of looking at how we would use these tools to use them for screening prototyping concepts. Now, why would the department make an investment like this? The department needs to get its under better buying power 3.0. The department needs to reinvest in itself in understanding how to be a smart buyer. In a very real sense, it's sort of given away part of the responsibility that it has to understand when it's getting an innovative idea. So I would submit to you that the smarter the department is in understanding innovation, the smarter and more likely it will be in recognizing when you bring in an innovative idea. It's not to compete with industry in any sense of the word. It's rather to understand when it gets an innovative construct. There's a layered architecture that I mentioned to you. Just a little graphic associated with that. Each of these pieces, this follows a very prescriptive idea. We've worked with Carnegie Mellon to develop this capability. We've got a very powerful Tradespace capability that's been instituted up on the HPC world. The HPC world, however, is not the right world, really. It's a great world to crunch numbers in. We've actually increased the ability to analyze or to develop alternative cases such that we can now generate about 10,000 of them in the time we could generate one in. Okay? So we've sped this process up enormously. Okay? We've done that by creating our own Tradespace capability over time. Now, this process is still very brute force. It is not nearly as elegant as I would like for it to be. There's still a great deal of room in this, and there's a lot of data analytics that still needs to be done in this. For example, let's say that we put together a Tradespace that had 2 billion entries in it, just combinations of, for a particular airplane, of all the different characteristics of an aircraft. Okay? How far it flies, different weaponry, et cetera, et cetera, et cetera, et cetera. What I would really like to be able to do with that, obviously, is I would like to be able to go back into that and I would like to learn from it. I don't really just want to design an aircraft. I want to learn things from it. Almost in a research mode. I want to understand almost rules of thumb, margins, if you will. If I want one more margin of speed, what does that do marginally to the other aspects of the aircraft. I want to learn those things. I want to understand the analytic expressions of those if I can. Next, what I would like to be able to do is I would like to be able to understand from that the inverse problem. What would it take to defeat those capabilities? Okay. It's a very powerful construct, all of which would be done well behind any number of layers of walls. Okay. We've built an infrastructure within this capability where we've actually built a cloud inside the firewall, inside the Department of Defense's Defense Research and Engineering Network, which is part of the HPC modernization program. That's where all of this has been stood up, and all of the contractors that work for the Department of Defense and all of the defense agencies that need to be able to get to this capability can get to it under DRAM. And that's a very controlled environment for us. So we've stood that up, and we've stood a cloud up. It's a regular cloud, and that is the best place for us to do our analytics, not the high-end big number crunchers. Okay, it's one of the things that we found. We've got this environment that we're simulating, and we're building that capability up. We're very fortunate to have much of the land data because we keep that for the Army in my organization. We need to work with the Navy and the Air Force. We have not started doing the space data yet. We do not have all the bathymetry data worldwide yet from the Air Force, from the Navy. Applications. We've done several. The one that I want to bring to your attention, we've done a couple in the rotorcraft world that are pretty interesting. The one that I really want to draw your attention to for the sake of time, let me see if I'm back up here. Working with the folks that work rotorcraft for the Army down in Huntsville and out at Ames, when Boeing redesigned the CH-47, which is the Chinook, it wound up losing 2,000 pounds of thrust. Army wanted that back. So the folks came in from Boeing and said, with their own IRAD money, and said, well, here's what we've done. We've redesigned the blades, and we believe we found a way to do this. The test and evaluation folks said, well, we don't have a way to really put that out on the test range right now. But I tell you what we will do. We're willing to entertain the idea of you guys of DoD using the new CFD codes that have come out of this program, and the name of that code is Helios in this particular case, to evaluate exactly what you see about those blades. And so we were able to use that code, Helios, to evaluate the worth of those blades, and what we found was pretty interesting. We found that, in fact, the blade design did get back the 2,000 pounds of thrust. We found that for particular conditions, that in some cases the range was lessened, and for other cases the range actually could be increased for particular atmospheric or environmental conditions and for particular mission conditions. And that information was reported back to the test and evaluation people, who then used that for the first time to make some of their decisions regarding whether to go forward with a particular blade design. Okay, that's now in their hands. That's a major success story for a very conservative group of people within the department. Okay. The Navy has used this approach to evaluate up to 19 million alternative designs of the small surface combatant. From that, they came up with 5 major designs, and those designs were reported all the way up to the Undersecretary of Defense. The thing that makes all of that work, though, is not the Tradespace analytics. That's a helper, but the thing that makes that work is the belief that there's some truth somewhere, and that truth in this case has been derived out of these CREATE tools. There are 5 aspects of CREATE. CREATE AV is the air vehicles component. There are major pieces of that. I believe I've got another slide on that in a second. CREATE ships. There are DoD and industry teams involved in each of these. There are formal testing regimens that each of these go through. Some of you perhaps have been testers associated with some of these codes. Create RF is for radio frequency. It basically was created to work on the antenna interference problem. MG is a meshing and geometry component, basically creating what I would call enabling technologies. And then the Create GV is for ground vehicles. The first three are the most mature, probably 5-6 years or more in their maturity. The GV is probably 3 years, I would say, as it goes along. This is an expanded view of what's in the AV world. The principal components of it of AV are Kestrel and Helios, although there's a third component, Da Vinci, that's shown down below. These were designed by people who do design, who do CFD. So there are helping capabilities, how you mesh, how you create alternative designs, things of that nature, how you parameterize, as well as the actual solvers that are involved, how you use them on the large-scale MIMD-type architectures themselves, things of that nature. The program itself that created this, sorry to you keep using the word create, the program itself, Create, was envisioned as a 10-year effort. And it is in year 6 or 7, Doug, 6? And we work very hard to protect that program because that investment is an investment that the services were not making. This is more about the rotorcraft. I'll leave this to the audience to read on its own for the sake of time. These are the industry partners. They're part of the ERS effort. Each of these industry groups are involved with us. NDIA has been very good in helping us put on industry fora. We've had several sessions that have brought us connections with industry. Lockheed Martin, BAE, and Raytheon are all under contract and all bringing IRAD capabilities to the table to work with us. Boeing is talking with us along those lines, as is Northrop Grumman, which is unfortunately not shown here. So we do have an industry component. We have talked about how to protect their IP. We believe we have a way to do that, which is a pretty straightforward way, which involves protection through migration of data as opposed to protection through exposure of the models themselves. This is our strategy. I show you this so you can all tell somebody that a DoD guy showed you that he had a strategy. Now you all feel good about yourselves. Okay. These are the areas we've got left to work on. There are many. We've been working on this for about 2.5 years. We've made a lot of hay while the sun shines because we had a lot of good stuff to draw from other places. A lot left to do. And with 16 minutes left, I will stop and ask you if there are any questions. If not, I'll just stop talking. Do any of them say, is the boy crazy, or?
So we have a system that allows people to ask questions, and then people can vote on the questions. So we have some very popular questions, one of which is, who will be doing these analysis? That is, who do you see as the sort of engineering tip of the spear in this project?
There are already groups of people that do these for the department. For example, in the area of naval architecture, the folks at Carter-Rock in the Navy in Bethesda, Maryland, are the interface for the Navy that actually do these naval architecture designs. In the Army, the folks that actually do these types of ground vehicle designs are the Tank and Automotive Command folks, the TARDEC people in Flint, Michigan. They do a certain level, then they hand it off to certain program managers who then take it from there. So there are elements of these folks who already have these responsibilities, and we're trying to empower them to be able to do them more rigorously with the same level of effort that they do them now. In some cases, we'll have to do some training. In some cases, they're already trained.
This is a fascinating talk, by the way. I've learned so much. In the context of the work that you're doing, do you believe that the 8-year development of the B-52 would be longer or shorter than today? If you can sort of do that experiment of taking your process and applying it to a program like that.
So is the question whether the development will be shorter or whether the ultimate lifespan will be shorter?
It's actually just about development. Maybe you could address both.
So the development cycle has to be shorter for a number of reasons. We have to be able to get things to market and to use, I believe. That's ultimately a policy question, but technologically, things have to turn over much more quickly because technology in and of itself is much more disruptive than it was 30 years ago. From the standpoint of reuse, we would like to be able to reuse things we'd like to multiple purpose them if we had the option, which would suggest that we would perhaps use a platform in several different ways, in which case we might keep it a long time if we had the luxury of doing so.
Mm-hmm. So how can the ERS tool be used to train engineers?
Well, that's where it's really amazing. We actually did a project with the Carter Rock folks where we took two teams, one that was led by a 30-year naval architect and his known team, and one with a group that had only 2-year and less folks, 2-year experience and less. We gave them, the Navy actually set this up for us. The first group did everything exactly the way they had always done it. And the other group took the tools and followed the set-based approach of the way they did it. In the middle of the design they were doing, we perturbed on purpose the design. We changed the game. We changed the rules of the game. The first group, with the 30-year architect, survived only because of the 30-year architect by their own admission. He's retiring, by the way, in a month. The other group simply went back to their database, reanalyzed their database, pulled a new design out of it, and just kept right on going. And what was really interesting is when the two groups got done, the design that the 2-year group had actually had less risk to it than the 30-year group did, although both of them were about the same expense.
So that example, I'm going to add my own question here for a minute because this is intriguing. That example shows the strength of the approach. What would you consider a weakness of the approach that still has to be sort of, people have to have an awareness of or a caution about?
The approach is strongly dependent on having enough modeling power and capability in it to be able to cover the things that you want to cover. There are many, many other aspects of the analyses that we need to do to an airplane beyond whether it flies.
Yeah.
And so we're just at the tip of the iceberg in terms of the analyses that we're capable of doing in ERS right now. We can absolutely tell whether it flies, how far, how long, how sideways, how upside down. We need to be able to tell what it can, who sees it, who it sees, those kinds of things for DoD applications. And we haven't yet been able to pull those types of models in. And those models all have to be fully validated. And in some cases, those models belong to, are highly proprietary. Mm-hmm. And so how to deal with that proprietary nature and still get that validation so that we have a trust level for those data is something we still have to work.
That sounds like a lot of work yet. Here's a question about the Defense Acquisition Guide. It appears to be regularly used to regularly updated to address a number of your issues. What 3 things do you believe need to be addressed in the guide?
I really can't answer that.
Okay. Oh, here's a question. Someone from NASA, or a few people from NASA out there. Can NASA get access to Create? Is it pretty just DOD, or can...
Doug, can NASA, is there any reason that we couldn't work with NASA to, I mean, we should probably take that offline and talk to NASA leadership about how to do that.
I think a few people in the audience are interested. As modeling and simulation tools continue to improve, how do you view the importance of subject matter experts' involvement in the design process, and do you have any recommendations of how that can best be achieved?
So, subject matter experts will never, say this more positively, I don't want to live in a world where we don't have subject matter experts. I don't want AI. The whole process of validating and verifying models requires that we have modelers. I'd a lot rather have a good modeler and a bad model than to have a good model and a bad modeler. Okay. Right? So we don't want people who don't know anything about modeling trying to model.
Okay. Here's a question. What's the difference between resilience and mission assurance?
Mission assurance is actually getting the job done. Resilience is getting many jobs done. It's being able to do a large number of things. In some cases, being able to do things for which the aircraft, in the case of an aircraft, was never designed.
So it's sort of a flexibility measure to a certain extent.
It's really got 4 aspects to it. It's the ability to adapt, to recover, things like that. So it's more than that. You can apply resilience to what a levee does when a hurricane goes by, right? There are a lot of different aspects to resilience that are beyond the idea of it. It's not just doing the mission for which it was designed. Now, if you design something to be resilient from the beginning, then in a sense, mission assurance and resiliency could be the same.
So mission assurance becomes sort of a subset of the resilience at that point.
It is now, yes.
Yeah. Can you quantify the impact of ERS on a real development program? I think you gave us a little bit of an example of the helicopter.
We're new enough that we can't quantify it. We can only qualify it. We've got some real good anecdotal information of where we've contributed. In the same way that we have about 75 acquisition programs where our Create tools have supported those. We don't have an end-to-end yet at all because the programs are 20 years long. And I will be long dead before we get one done.
We'll take a couple more because I know people have their technical sessions coming up. Why not change DoD 5000 to minimize development processes to prevent requirements creep rather than make the contractor fix it on the fly? I think this might be is this a little off topic?
So, no, I mean, that's a little bit policy oriented, and I can't answer that, but I can only say that we know that requirements are changing all the time, so we can't very well tell the requirements not to change. They are going to change.
Yeah, inevitably. And then we'll close with one looking forward. Is ERS being taught in universities today, or the concepts? So basically, how are you planning for the next generation workforce education so that students can come into this program?
So we have connected to some schools. I didn't mention the schools, which is probably an error on my part, but there are schools that are teaching systems as opposed to just systems engineering, which I find to be 2 different things. Systems thinking is taught in a lot of places, not just in systems engineering. So there are parts of Georgia Tech and parts of MIT and places like that where they're teaching systems thinking. And you can tell by the way the professors and the students approach you. And we're connected with folks like that, and they're parts of our teams.
Very good.
So we're finding them. We need to find more.
Well, thank you very much. I know we lost a few people who are rushing off to their technical sessions, but we really appreciate your time, and thank you for coming to visit. And it was really very fascinating. I know I learned a lot, so thank you.